Okay, so I guess I'm audible. All right. Yeah. So, good evening, everyone. I am Shouharda Ghosh, second year PhD scholar in the Department of Electrical Engineering at IIT Gandhinagar. So, I'm the course TA for the NPTEL course on uh, signals and systems, and this is week 9. Just week 9 for signals and systems course. All right, so let's see what has been covered in the previous not previous, this week 9's content. Let us jot them down. So the topics covered are: number 1, Fourier transform of periodic signals, then Fourier series representation in continuous time. Then we had a look at some Fourier series properties, and LTI system response for periodic input signal, and finally some examples of Fourier series in continuous time. All right, so actually if you look, we have covered a lot of content in this course, and since we have already covered Fourier transform and Laplace transform, you might have observed that there are a lot of, except a few things such as the ROC stability and all these stability things, a lot of the properties of signals, uh, let let's say how a signal shifts in time and the corresponding phase change in the frequency domain, and so on, scaling factor and all, differentiation, integration, multiplying signal with time and all that stuff, convolution and multiplication of signals, vice versa. So many of these properties actually turn out to be similar for Laplace transform and Fourier transform. And what we shall be doing, so actually in this course uh, the generic things, that is the Laplace and Fourier transform, has been covered first. So these weeks and the upcoming weeks will be much simpler compared to how you felt in the initial days of the course. So these assignments or these days will take less amount of time, but still we shall revise things because they will be useful for your exams as well as the later courses that you will be taking in the electrical and electronics degree. So what did we study till now? We studied about the spectral analysis of continuous. Okay, so I think I should change the color now. So till now we have covered spectral analysis of continuous and aperiodic signals. So whenever we studied Fourier transform, which if you look, x of omega was integral over minus infinity to infinity x of t e to the power minus j omega t dt. So there was no restriction on xt, and in fact it was considered that it can be either this or something like some variation can be there, but it was did not have any period. It was generic signal and it was continuous time. We are dealing with continuous signals for now. And when we looked at Laplace transform, we had this x of s is minus infinity to infinity x of t e to the power minus st dt. So all of this hold for signals which are continuous and aperiodic. Okay, continuous signals to be more general. Now and why am I saying the aperiodic thing? Because if you actually look at the Dirichlet conditions, so one of the Dirichlet conditions, or DC in short, states that the over the entire time over the entire number line, the timeline from minus infinity to infinity, if you take the absolute value of xt dt, that must be less than infinity. So the area under the signal must be finite. Okay, and if you look very carefully, there were special cases, and one of the special case was sine and omega t and cos omega t. So these were periodic signals, and you see we did not actually get to this sine omega t cos omega t directly. We actually did certain modifications or certain assumptions or some pushing from behind, that we assign these sine omega t and cos omega t these spectrum. And the spectrums are not if you see the spectrum of sine and cos, they are not normal functions. They are made of impulses. Impulses are not the so-called standard functions whose properties of differentiability, integrability and finiteness are valid for these cases. So these are just doing it for the sake of making our analysis complete, and because sine omega t and cos omega t are very important functions to be dealt with. But if you see in general, continuous time signals, continuous time signal, sorry, it should not be continuous time, be periodic signals violate this. So what is a periodic signal? How do let's give a small example of a periodic signal. So let's say the triangular wave that you can see over here is our periodic signal. So you see the signal is nothing to be scared about for not being able to do the spectral analysis. See, if I consider a finite window, and let's say the window has to be of the time interval t, and this entire window repeats itself. The window length is the time period of the signal. Alright, so if I'm sticking to this small window, then and forget everything, and I do it spectral analysis, so wouldn't that be useful? So what happens actually is that now when we work with continuous time signals, we consider the signal within the window of the time period and then extend the properties. Okay, so periodic signals are a special case of continuous time signals, and correspondingly we have their spectral analysis or the representation. So what happens, I am not going to the proof and all that, how do we get the Fourier series and all from these things. So xt equals to x of t plus t for all t belonging to set of real numbers, or t belongs to minus infinity to infinity. This condition implies that our signal is periodic. All right, and what is the Fourier transform or the Fourier transform representation? So we say that such a signal xt can be, so these are periodic signals, and what is the most basic periodic signal that we know? Sinusoids, or cosine waves, or sinusoids, or exponential complex exponentials, right? So just like the intuition of Fourier transform, where we take in all the all possible frequencies, right, from minus infinity to infinity or 0 to infinity, and then their conjugates in case of real signals. So we take all possible frequencies, real frequencies, and then assign some weight to that sinusoid, and then add all of them up and we get the signal. In this case, this is periodic. So what will happen in this case? We will not be using all the possible frequencies. We will be using xt will be made up of periodic signals with frequencies same or multiple of this frequency. That means here it is repeating with a frequency f naught equals to 1 upon t. Okay, so we will build this signal up with constituents, with sine and cosine, with frequencies f naught, 2f naught, 3f naught, and so on. So these are actually called the harmonics, or the multiples of the original signal. These are called harmonics of f naught. So how can we write xt? So one way of writing xt is in terms of summation of complex exponentials. How is that written? Xt is summation over all the indexes k minus infinity to infinity ck e to the power j k omega naught t. Okay, so this is a complex exponential with frequency k omega naught, where omega naught is k to 2 pi upon t. All right, now, or you can also write it as 2 pi times k f naught. So you have DC signal 0, f naught, plus minus f naught, plus minus 2f naught, plus minus 3f naught, and so on. Okay, so it's made up of complex exponentials. That's one way of writing. So this is called the complex exponential Fourier series. xt is summation of k equals minus infinity to infinity ck e to the power j k omega naught t. So what is the frequency component of the spectrum? The spectrum is actually the this value ck is 1 upon t integral over any period of length t, any window of length t, and it will be integrated over xt e to the power minus j k omega naught t dt. All right, and how will the spectrum look? When we draw the spectrum, we have to always draw two parts, magnitude and phase. So the magnitude this is mod ck, and this is k. So we'll be having discrete indices 0, 1, 2, 3 and so on, -1, -2, -3 and so on. So let's say at 0 we have something like this, 1 we have something like this. I'm assuming it's a real signal, so it will be symmetric. 2, let's say something like this. 3 we have something small and so on. Okay, so these are the, so this is the magnitude of the signal, DC signal at frequency, DC frequency. This one is the magnitude of the sinusoid that exists as frequency f0, this one at 2f0, this one at 3f0 and so on. Okay, and how will the phase spectrum look like? Angle ck, so this will look like at 0, let's say it's it's 0, so you can't have any phase, that's a real signal. At 1, let's say something like this, at 2 something like this, 3 something like this and so on. At -1 it has to go down because it's anti-symmetric. Okay, remember the property x of omega equals to x star of minus omega. So when you check the phase part, so you actually get angle x of omega is minus of angle x of minus omega. Alright, and this one the same thing will actually hold for the since it's more general, the Fourier transform is more general, the same thing will hold for the periodic case. 2 will go up, 3 will downwards, and this continues. Okay, so this is how the spectrum looks. So unlike the previous case, in the aperiodic case, we used to have spectrums which looked continuous, and in these cases spectrum which used to look something like this. That is not the case over here. Here these are discrete bins. Now this was the complex exponential Fourier series. Now there is another thing called the trigonometric Fourier series. What happens here? Here we write xt as this is a DC term, a0 plus summation over k equal to 1 to infinity ak cosine k omega naught t plus bk sine k omega naught t. So you see here we are writing it in a different way, but it's much more clear, it's much more intuitive, that we are writing the periodic signal as summation of sinusoidal and cosinusoidal harmonics. Alright, where a naught is the DC or the average value, xt dt, ak is 2 upon t together over t xt cosine k omega naught t dt, bk is 2 upon t integral over t xt sine k omega naught t dt. Okay, so these since cosine is a real signal, is a or even signal, these are also called the even coefficients. And these are called the odd coefficients. even in terms of even and odd signal, not the even number and odd number. So I am using this term with a bit care. So whenever you see, you have to understand when they say even and odd harmonics. So whenever they say even and odd harmonics, be careful that they are talking about the even numbers. Actually, sometimes you'll get question that the even harmonics of the signal are 0, the odd harmonics of the signal are 0. Then that doesn't mean these that doesn't mean these and these even and this odd. It means that the k is even or the k is odd. Okay, so you should be a bit careful about this. So this was revision, although much more you can visit the lectures. Now I shall solve some of the previous years assignment. Question 1. Determine the Fourier series coefficient c of -1 for xt equals sine 3t. Okay, now you will come across such questions very frequently, where you will find xt as summations of sine and cosine directly. There will be multiple sine and cos terms, and you will be asked to find the Fourier series coefficients, the complex exponential ones. Okay, so in those cases, don't directly jump into the formula. So let me give you another example. Let's say xpt equals 2 sine of 20 pi t minus 10 cosine of 30 pi t plus 5 sine of 5 pi t. Okay, so this can also be one example. Okay, I'll solve this later if you want. So for such questions, don't jump into ck equal to 1 upon t integral t xt e to the power j k omega naught t dt directly. Don't use this. I mean, whenever you see only signs, then don't jump into this. What should you do actually? See, let's look at the first case. xt equals sine 3t. Now what is sine? Sine x is e to the power jx plus minus e to the power minus jx upon 2j, isn't it? I'll simply use this e to the power j3 minus e to the power minus j3 upon 2j. Okay, now let's look at this. The fundamental is omega naught equal to 3 radian per second. Okay, so now omega naught is 3. So what are the multiples of 3 that you can see in this? So it will be, so you can have terms of the form e to the power j plus minus j3 e to the power plus minus j6. Okay, I forgetting the time. 3t, 6t, j 90, and so on and so forth. We can have these exponential terms. Now this corresponds to k equals to 1, c plus minus 1. This corresponds to c plus minus 2. This corresponds to c plus minus 3. Alright, so now what are the terms visible? X of t e to the power, this is 1 upon 2j e to the power j 3t. This is the first harmonic, the positive one. So what will I call this? I will call this C1. And why am I saying this? Because xt has to be represented as summation over k ck e to the power j k omega naught t. Alright. Okay, so I am trying to find out the ck's by looking at the exponential terms, and then we have minus 1 upon 2j e to the power minus j3, because this is a negative first harmonic, so this is c of minus 1. So what do we get? We get c of minus 1 equal to how much? Minus 1 upon 2j, and this is our answer. Okay, now let me use the more elaborate one as well. Copy image, paste image. Okay, so now in this case there are multiple frequency components. Okay, so first you have to check whether it's periodic or not. When there are multiple signals, then what do we check? We will check that, let's say their frequencies f1, f2 and fn. Okay, we will check the ratios fi upon fj. Okay, if all of them are rational numbers, if all the ratios turn out to be rational numbers, that means it is of the form p by q, where p and q are integers, positive integers, and q is not equal to 0. In that case, when all the possible ratios of f1 by f10, f2 by fn and so on, you check all the ratios, so in that case we will say that this is the periodic signal. In this case, you don't need to do that. You see very carefully what are the frequencies available: 20 pi t, 30 pi t and 5 pi t. Look at the smallest one. The smallest one is 5 pi t. This is the six times, and this is 4 times. Okay, so clearly see there is the harmonics of 5 pi t. So fundamentally omega naught is 5 pi. Okay, now we'll apply the same principle over here and decompose xpt. xpt is 2 upon 2j e to the power j 20 pi t minus e to the power minus j 20 pi t minus 10 upon 2 e to the power j 30 pi t plus e to the power minus j 30 pi t plus 5 upon 2j e to the power j 5 pi t minus e to the power minus j 5 pi t. Okay, now let's look at it term by term and arrange them. These are the first harmonics, these are the 5 times 6 is 30, this is the sixth harmonics, and this is 20 by 5, this is fourth harmonics. So 5 by 2j e to the power j 5 pi t plus minus 5 by 2j e to the power minus j upon 5 pi t plus 1 upon j e to the power j 20 pi t plus minus 1 upon j e to the power minus j 20 pi t plus minus 5 e to the power j 30 pi t plus minus 5 e to the power minus j 30 pi t. All right, so let us point what is what. This is c1, this is c minus 1, this is c4, this is c minus 4, this is c6, and this is c minus 6. So if I tabulate them all, c1 is 5 by 2 angle minus 90 degree, because that's minus j. C of minus 1 is 5 by 2, that's minus 1 upon j, so that will come up and it will become j, so that will be 90 degree. C of 4 is 1 angle minus 90 degree. C of minus 4 is so that's 1 angle 90 degree negative. C6 is minus 5 or 5 angle 180 degree, and C minus 6 is also 5 angle 180 degree, minus 180 degree, both of them are the same. Okay, so these are the spectral components present in your signal. So a question could have asked you like find C1, C minus 2, C3, that could be one type of question. Okay, or they could have given you various spectrums. Okay, and you would have to choose which spectrum matches that the signal. So in this case the spectrum will actually look like, so if I take mod ck, k over here, 0, 1, 2, 3, 4, 5, 6 and so on, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. This is 0, this is half of 5 or 5, 2.5, 2 is 0, 3 is 0, 4 is 1, 5 is 0, 6 is 0, 6 is 5, sorry 6 is height 5. These are all the heights. This is 5 upon 2, this is 1, this is 5, this is also 5 upon 2, minus 2, minus 3, 1, minus 5, this is also 5. This is the magnitude spectrum. And now let us look at the phase spectrum. Zero, 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5 and minus 6. Okay, so sorry, at 1 we have plus 90 and minus 90. Plus 90 degree and minus 90 degree. Okay, I think I should have been reversed. Minus 90 degree plus 90 degree minus 90 degree plus 90 degree (180 degree) minus 180 degree, and this is the phase spectrum. Okay, so you see I have also given you an example of how to calculate, like how to obtain the spectrum from this. Okay, in fact you do not need to draw this. Once you are able to get to this entire thing, you can easily check the spectrums and verify which one is correct, which one is wrong. Okay, so this is a very good and short way of solving this without going for the integral stuff. All right. And then the next question is, I have actually told the answer of the next question during this explanation. If yt equals to a x1t plus b x2t with period of x1t as t1 and x2t as t2, then the Fourier series for yt is only possible in case option A, t1 plus t2 equals to m for m belonging to the set of integers, b, t1 times t2 equals to 1 upon m for m belonging to set of integers, c, t1 into t2 equals to m for m again in the set of integers, and t1 by t2 equals to m for m belonging to set of integers. Okay, so let me check once. Yeah, so if you remember carefully, we had talked about this, right? That we can write the frequencies as rational numbers, only then the signal is periodic. Okay, so which is the one that resembles closely? It's option D. T1 upon T2 is m. So actually they are talking about the fundamental and harmonic and those concepts. Okay, so although it's given T1 upon T2 equals to m, so I'll give you a case where there's a periodic signal, but this need not be an integer. For example, let's say xt equals to cos of 40 pi t plus sine of 60 pi t. What is the fundamental harmonic in this case? Here it's 20 hertz actually, and this one is 30 hertz. So if you want to check the fundamental harmonic, what do? We take the highest common factor. Highest common factor 20 and 30, what is that? It's 10. So basically these are harmonics of 10 hertz, that is 10 hertz is coming up as 20 hertz and 30 hertz. So the period t should actually be 1 upon the fundamental, that is 1 by 2, that is 0.1. Okay, so x of t plus 0.1, this is just for the case of verification, nothing else. 40 pi times t plus 0.1 plus sine of 60 pi times t plus 0.1, this is cos of 40 pi t plus 4 pi plus sine of 60 pi t plus 6 pi. So both 4 pi and 6 pi, these are multiples of 2 pi, so we have essentially the same shift of 0. So our signal is indeed periodic. You see over here, it's not necessary that t1 by t2 equals to m, although they have given in this previous year's assignment. It's a special case. So if I once again I ask you to break this down, so you will get c2 and c of minus 2, and here you will get c3 and c of minus 3, because c1, which corresponds to 10 hertz or 20 pi t, that 20 pi t term is not available in this x of t. So this is one thing to keep in mind. A signal may be periodic, but this is an example where fundamental is absent, but harmonics are present. Okay, so in general actually this should be t1 by t2 equals to m1 by m2 for m1 and m2 in the set of integers. Okay, so yeah, that's it. Then question number 3, determine the Fourier series coefficients ak for yt which has a period t where yt is equal to 1 for mod t greater less than t1 and 0 otherwise. Okay, so we actually need to find the complex exponential coefficients. So let us draw the signal first. So minus t1 to t1, it remains like this, and it should be mentioned that t1 is obviously less than t, the period. From t to 2t you have this is 0. No, this should be t, this should be t by 2, this should be minus t upon 2, this should be 3t upon 2, and this is a width of 2t1. So you see this is a square wave that has a width different from the period, and this width upon the period, you see I have a window of size, let me use different colors. I have a window of size t, and here I am utilizing only a smaller part of it, 2t1. So this ratio is called duty cycle. It is the on time divided by total time times 100. This is in percentage, or 2t1 by t times 100% for this question. Okay, so the normal square wave that we are familiar about in digital, if we study later digital electronics, the microprocessors, so they generally they are 50% duty cycle, so they are on for 0 to t by 2 or some minus t by 2 to t by minus t by 4 to t by 4, and for the rest half of the time they are in the off state. This is the duty cycle. Just stated it because may not required, but for GK, general knowledge, general electronics knowledge for this question. Now I'll show you the CK value. CK is 1 upon t. What would be a suitable range of integral? The suitable range of integral window is this, because this is a symmetric window, and when you have symmetric things, a lot of the integrals become beautiful. We can apply symmetry properties, we can apply the e to the power these sinusoids, complex sinusoids can turn into real stuff. Okay, so I'm taking the integral window from minus t by 2 to t by 2, and this yt e to the power minus j k omega naught t dt. Omega naught is 2 pi upon period t, and if you see it's actually on from minus t1 to t1 only. Okay, so 1 upon t integral over minus t1 to t1, yt is 1, so I am not writing it in this interval, e to the power minus j k omega naught t dt 1 upon t minus e to the power minus j k omega naught t, denominator we write j k omega naught minus t1 to t1 1 upon j k omega naught t e to the power j k omega naught t1 minus e to the power minus j k omega naught t1. So I need, this is again the sin x form, so I need to take 2 from somewhere, so 2 k omega naught t e to the power j k omega naught t1 minus exponential minus j k omega naught t1 on 2j. Now look at this, omega naught into t is 2 pi, so 2 upon omega naught t will be 1 upon pi. So what will I get here? 1 upon k pi, and what will be this over here? Sin k omega naught t1. Okay, this is sin k omega naught t1 by k pi, or 1 upon k pi sin 2 pi k t1 upon t. Okay, so you see over here, I can also write 1 upon k pi sin k pi delta, where delta is 2 t1 upon t, this is the duty cycle. Okay, so how will this actually look like? This will actually, since this is a discrete time signal, let me sketch the contour. So 0, 1, 2, 3, 4, so on, minus 1, minus 2, minus 3, minus 4, minus 5, this 3, 4. Okay, so the spectrum will look very much similar to the sine thing, but it will be the discrete form. So something of these are the forms of signal that you will see in case of the pulses. Okay, so because now on you must get familiar to this, because the same kind of functions are associated with pulse, and whenever you have pulse you will see these waveforms coming up. Okay, so that's our answer, 1 upon k pi sin 2 pi k t1 upon t. Okay, this is a simple question, just the calculation was there, nothing else. Then we have our next question. Time shifted signal x of t minus 3 will exhibit the Fourier series coefficient ak as option A, ak e to the power minus j 3k omega naught, b ak e to the power minus j k omega naught upon 3 ak upon 3 e to the power minus j k omega naught upon 3 3ak e to the power minus j k 3 omega naught. Okay, so I won't be using property. I will do it from scratch, so that if you forget properties, you will be able to do it in the proceed in the same way. So let the Fourier series coefficient be dk. dk is what? 1 upon t integral over time period t x of t minus 3 e to the power minus j k omega naught t dt. Let me put z equal to t minus 3, dz equal to dt. So t is what? T is z plus 3 actually. Okay, 1 upon t. So the limits, even you are shifting t to z, but then the length of the integration period will be capital T only. It's just that the window of integration is shifting towards the right side. X of z e to the power minus j k omega naught z plus 3 dt. So now I take out the constant term e to the power minus j k 3 omega naught 1 upon t integral over t x of z. Okay, so this should have been dz e to the power minus j k omega naught z dz. And what is this? This is nothing but our original exponential Fourier series. Here they have written it as ak, so I will write it as ak. So it will be ak e to the power minus j 3k omega naught. So this is our correct answer. So A matches, and in general you can write for x of t minus capital T, the corresponding ak becomes ak e to the power minus j k omega naught t. Okay, it's the same as the Fourier series, normal Fourier transform. Now let's look at question 5. A time scaled signal x of 3t will exhibit the Fourier series coefficient in terms of ak as option A 3ak, option B ak upon 3, option C ak, option D a of minus k. So I will be doing this from scratch because I also do not remember most of the Fourier series formulas, so it's a good habit to use from scratch. You can do it very fast. Here I am explaining, so I am doing it slowly, but in general you can do it. If you do it in rough, it will be very easy. So let the series be dk. dk is 1 upon t integral over t x of 3t e to the power minus j k omega naught t dt. Let z be 3t. Okay, so if z is 3t and let's say my integral is from, in this case I will write the integral for sake of simplicity and without loss of generality. Z is 3t, then dz is 3 dt, or dt is dz upon 3. Okay, that's the first point. Second thing, if you have something from 0 to t and repeating, this is, if this is your xt for only that small time, so now when you have xt upon x of 3t, what will happen? Your signal will shrink, right? 0 to t upon 3. So in this case, what is happening? You are still having the same signal, but it's compressed. There is no shifting. This the fundamental has changed. The fundamental, if in this case was 1 upon t, the fundamental over here will be still 3 upon t only. Will be 3 upon t, but then the harmonics will just corresponding harmonics will also be scaled by a factor of 3. Okay, and so now when you look at the Fourier series coefficient, it's in terms of k, it's not in terms of the absolute frequency, it's in terms of the index relative to the, we are in this Fourier series, we are doing it with respect to the fundamental harmonic, not the absolute value, we take relative to it. That's why the index k is an integer and not any absolute real number. Okay, so it essentially will actually turn out to be ak, but for the sake of completeness, let me do it. So if it was f0, 2f0, 3f0, these are the harmonics in the earlier case. New harmonics will be f0 prime, 2f0 prime, 3f0 prime. Okay, so in absolute value you would have shown it at minus f0, f0 and all, and here it would be at minus f0 prime, f0 prime. Okay, the spacings would have changed, but if you plot it with respect to k, the k is still the same because it's the first, second, third and so on. Okay, so now what will happen? Dk is 1 upon, so actually this integral will be incorrect. What we should actually do is this: dk will be 3 upon t integral over 0 to t upon 3 x of 3t, so it will be actually z now. So z e to the power minus j k, omega naught will become 3 omega naught and t will become z upon 3. Okay, and dt will become dz upon 3. Okay, based on these calculations. So 0 will change to 0, t will become t upon 3. So this cancels, so dk should be with respect to the period is, okay, let's say the period is t prime, one upon t prime integral over 0 to t prime x of y of tau e to the power minus j k omega naught prime tau d tau. Three upon t, t upon 3, y of t is actually x of tau so y tau will actually look like 0 to t upon 3 1 upon 2 and x of 3 e to the power minus j k 3 omega naught, and this is tau is tau d tau. Okay, so actually if you look carefully it will be ak only. If you look at this entire thing it will be ak. Question 6. An odd signal x of t will have the following property of Fourier series coefficients ak option A ak equals a of minus k, option B ak equals minus a of minus k, option C ak equals minus k, and D none of these properties. So if you look at xt can be written as summation ak e to the power j k omega naught t, and if you try to write x of minus t you will see that it can be written as summation minus a of minus k e to the power j k omega naught t. Okay, sorry, the minus sign will not be here. Now we know that x of, for an odd signal, x of t is minus x of minus t. In order to do that, what should we do? We should equate the Fourier coefficients. This is ak equals minus, and this one is minus a of minus k. So the Fourier series are odd. Fourier series also behave in the odd way. So this is the answer. In general, actually, if you look into it, it should be C of it should actually be C of C star of k is minus of C of minus k, because remember, for an odd signal x of omega is okay, so ak is 1 upon t integral over xt to the power j k omega naught t dt, dk is 1 upon t integral x of minus t e to the power j k omega naught t dt. Let me put tau equals to what will that be? This will be, if I replace xt, it will be minus x of t e to the power j k omega naught t dt. What is this? Minus 1 of 1 t x of t okay, so I should actually change the limits of the integral also, so that would make it easier. 0 to t dk 1 upon t integral 0 to t x of minus t e to the power minus j k omega naught t dt. Input z as minus t 1 upon t 0 to minus t x of z e to the power j k omega naught z minus dz. Now this is minus, so I can reverse the integral and write from minus t to 0 x of z e to the power j minus k omega naught z dz. So this is actually a of minus k. So if x of t has Fourier series a k, x of minus t will have Fourier series a of minus k, and since x of t equals minus x of minus t, correspondingly the Fourier coefficients will also behave in the same way. Okay, so this is the solution. A of k is minus a of k. Now let's move to question number 7. Assuming h of t to be the impulse response of a system, rather of an LTI system, x of t as the periodic input to the same and the output yt equals to xt convolved with ht. If ak is the Fourier series coefficient, so it seems that in this course the term ak has been used to refer to the exponential Fourier series rather than ck. Coefficient of x of t, what is the Fourier series coefficient yt. Okay, so in order to solve this, we will be using the fundamental and important property of LTI system, that is, for any LTI system with frequency response h of omega, okay, this is frequency response. So if I apply a sinusoid a sine omega naught t as the input, the output yt is what? It will be amplified it will still be a sinusoid of the same frequency, but it will be amplified by modulus of h omega naught and a phase of h omega naught. Okay, so that's it. Now what are we saying? That xt is actually summation of complex exponentials ak e to the power j k omega naught t. Okay, each has a frequency omega equals k omega naught. What is the corresponding response? The corresponding response is h k omega naught. This is a complex number. Now what will happen? This is the, we know that y of omega equals x of omega times h of omega. In the frequency domain is the multiplication. So what will happen? This is simply like a gain term which will be added to the frequency term of xt. So your yt will eventually turn out to be a k h of k omega naught e to the power j k omega naught t. So the Fourier series representation, the coefficients are a k h of k omega naught t. All right, now let's look at the final question before concluding. The Parseval's theorem is used to measure dash of a periodic signal and the resultant value gives dash. So actually, if you have gone through the lectures, Parseval's theorem applies everywhere. It's for continuous time signals, whether you are looking in the Fourier transform domain, Fourier transform, or in this case continuous discrete signals also, it will be the same. Okay, so what does it actually give? It actually gives us the energy of a signal. And what is the energy in this case? How do we calculate the energy of the same this signal? Periodic time, it will be integral 0 to t mod of x of t whole square dt. Okay, and what will the value be? The value will be summation k equal to, well, it's actually, although they mentioned the answer as energy, it should have been actually power, because periodic signals are not energy signals, they are existing throughout, so you cannot have finite energy, they are power signals. So it will be essentially be 1 upon t this thing. So it will be minus k infinity to infinity mod of a k square. Why? Because a single sinusoid a k e to the power minus j k omega naught t, a single this one, if this is x naught t, its power is mod of a k square, right? A single term. So when you have all the things clubbed together in a summation, then its power will also be summation of mod a k square. Okay, so I hope you have understood whatever I have tried to explain in today's session about periodic signals and their spectral analysis through Fourier series. Okay, thank you very much for your attention.